also in math logarithms, labs, and so on. We will look into this in slightly more detail. Since it is a high level abstraction, this particular library is a really high level abstraction, and therefore you can code this code seamlessly. The goal is like that, seamlessly code that distributed with a minimal programming effort. So the objective is to basically give the developers, so the way they define this within the application, that time is or their properties. So it is essentially nothing but an STL. It is standard once it comes, it is an extension to the core parallel program. And it really uses generative programming, it uses containers of the STL iterators and various data transfer units. And one of the bigger meaningful tasks have been programming is that you have to copy your code or data from the CPU, and unless you do that carefully, things might be messed up and something that taken care of. So let us look at this class library. This is, as I said, it is very similar to SQL. And as you know, in SQL, there are three dimensions: one considered and the iterator and the algorithm. These three dimensions are completely different, which is why I to here mismatch. That's the beauty of it here. So in class library, what happens is that the container side, there are containers like device vector container, and every container can have device vector features of code. But device vector means that it works with device and the host vector means it works on the host. There are features like EPC data transfer, where you can just do a simple assignment from device to host and so on, and the data transfer will take place. And it is compatible with the library because a lot of people are familiar with this and they should be able to make use of this, which is why they are compatible. From the algorithm side, there are many parallel algorithms. Like, for example, one of the very popular algorithms is reduction and the copy composition of an array or a data structure. Doing a prefix sum, sorting, these are all available out of the box, and you can also add your own algorithm. There are similarities, for example, with this here you have got sort, often not exactly the same thing sort. Now, iterators, as you know, they are pointed to the array elements. So both here is the both devices in the operator, and two iterators can actually do the memory access. So the classic way of handling pointers and then creating distinction between the host pointer versus the device pointer is largely though not completely different, but significantly. So let us look at this particular example of container. So if you want to write to the program on your left, here the example is that it actually hides the CUDA malloc and CUDA main process. I mean that you don't write it, but all the companies behind the scene. But as a programmer, you are not exposed to that. So all you do is some simple thing. If you look at the first line, is you are creating a host vector of size 2 of the data, then you are creating a device vector which is supposed to be decided for the device itself, and you see a simple assignment here in CUDA. So you are not dealing with the CUDA malloc and the and similarly, assign values to the device vector from the host is actually comes in the CUDA is simple here. For example, you have got a variable e underscore b in the host, and it is assigned to the device vector, and that will work. So, string compatibility is important. As I said that because you need to have a complicated, algorithm SQL and you can move some of them onto the device. Therefore, some compatibility is required. So, for example, you have SQL, it's a scientific library, and you have got a list here, and then you do some operation on the list on the host, and then populate that onto the device, and it's quite easy. So if you have written program in CUDA, you realize how complicated these tools like to be. Iterators again, here is a standard notion of iterator where the iterator has a begin and end pointers. And but interesting thing is that you can actually have a raw pointer to the device vector. So you could have this device vector and then can actually pass it to a simply the start using this kind of pointer count. And it is really not trivial if you use CUDA. So why do you need that? You may want to be pass this pointer to a CUDA kernel, because suppose you want to write your own CUDA kernel, and simply because the given pass library is not good enough, you have to write your own kernel. So in that case, how do you interoperate? So you basically can pass this pointer like this. But one important thing is that with respect to the pointer cannot be different from the host. One thing you must understand is that behind the scenes, there must be some way by which the code should know whether this pointer that it wants to be is a host or a different device. So that the code must understand. So this is why we have to do process. Now, algorithm features are also quite interesting to see that if you look at this particular piece of code which is on your left hand side, which is the native CUDA, all it is doing is doing a continuous content. And the first part of this code is getting the data and loading, loading the code data into just and then it is doing this kind of job. So now, it gets the data from host to device, then it does the actual activity. But if you have to do the same thing in class, it is actually, and then of course you are writing it back to the the global memory. As you know, global memory is memory that can access also very easily. So if you have to write the same thing in class, then it looks like your iterator storage as a device because you can do this on that device, on the data, one line, and just this. So the amount of code reduction time is significant. You just call it, and that's the kind of much simple and much easier to understand. Another important part is for the kernel fusion or the kernel margin. So sometimes, and I will talk about that later, that why kernel margin is an important area of research. So kernel margin often gives you a good performance there. So on the left hand side, here in the class, you can actually do this norm calculation. And one important thing is that if you look at on the left, so there is a function called square. Function is basically a function of it in the columns of ACM or even C++. It's an object that is struct, but it has overloaded operator, functional operator, and therefore it uses a function. So it's not function operator. And function operator advantage is that can actually store a string. So here is a function operator which is doing a square, and in fact it is norm calculation. So basically you have a device like this. Then you go to transformation on this, you call transform function, and you do a square root of, then you do reduction of the transformation, and then you do a square root. And that will be your norm of the array. However, if you see here, there are two kernels involved, one is transformer and the reducer. But that can actually cause performance, and that is actually reduced by on the right hand side by just combining these two. And what you can do is that you can just call that replay or transform reduce, which actually combines transform and reduction, and therefore it can gain performance. In some of the later slides, I will show that this itself is a good area of research. So, so what is the cool here? So the interesting thing is that this particular, as I said, is supposed to be codable, right? So if you look at this particular code, and then you can see that this particular code is being transformed and reduced. So this code is actually when you are writing code like this, you really do not know or you really do not want to know whether this code should be running on the GPU, CPU or processor. So you write it like this, and then there is a happy point here. You see that class underscore device, right? And here the value is class device. So this is your kind of giver that you use to just choose between certain device. So instead of CUDA, you just say that is so just because I say CUDA, then this code will be executed on. I mean, when I compile that, the code will be ready for TP. Instead of CUDA, if I say that it is to be executed on CPU, without changing this code, all you do is just take this particular value to the last device's CCP, and then the code becomes ready for CPU. Then if you change it to PDB, and it actually can do the details PDB, and it can run on any code. Same code can run all of them, and that's how they can achieve more coding. However, there are limitations. So, lack of articulation of data structure is very important, and it's here. Lack of support for the external memory and shared memory is there with and hopefully you can address later on. There are limits of algorithms. If you want to have your own algorithm, you have to write it on your own, and that may not be trivial. No support from pipeline. So while I have given a reasonably detailed description of our first that on the concept one, there are other work also where people are actually working on design patterns. So design patterns are quite common in computer design. They are working on design patterns for parallel architecture. And then these are the work that are happening there to get those patterns to support programming that the program becomes easy. So researchers are also evaluating how we exclude different kinds of design spaces in the context of parallel programming. What is the best design that I can have, which can be program effective? I will show one of that particularly here that we work on. People have talked about identity specific languages in context to come up with a to support the program. So this is primarily the work of design space exploration. Essentially, if you look at traditional software engineering research, where usability has been one of the main cost area where I try to design components to be usable, and that has been the most meaningful community. If you look at the physics community, they are also writing the program, and they also do not want to be rewrites again and again. So component-based design research can have extended direction in the context of LVC. And there are different design methodologies can be proposed Go, and so on. So that you can not only support component-based design, but you can also deal with basic performance. So one of the work that required our work, where what is suggested is that we have if you are really creating a large PC application, which consists of several components, and those components you have to just compose them into your plan, and that's not the outcome. You can actually writing the C program which is close to real lines, and it's components. So the people who are actually combining those components of body, they are experts in that way. For example, so people who are experts can possibly create the right test component. And so simply you as a developer, you can use those components and then compose them. First is that if you actually use the best highly optimized component, you get a highly optimized code. And the answer is no. It's not always true that any highly optimized component just every failure and compose it, you get the best possible answer. And that's what we have stored earlier, and that's one of our ACM Compute. So, for example, if you look at this particular molecular and scores, and these are the 7 products here, K1, then K2, K3, and levels, and K5, and K7. Therefore, why type of design process? How would you like to implement the K1, K2, and so on? Do you want to just have a global communication, or shared communication, or just what gives you the best result? So, essentially, what we have shown there is that, suppose somebody has given you those marks, K2, K3, and so on, and also told you that what were their performances when they were executed in isolation. Then, using that information, can be composed and get a good result. So, for example, can you just put give the case to the parallel? Can you combine the 5 cases in K7? What after obviously those experiments, these were the 3 possible answers that we got here. What investigate? The first one is the trivial example, just trivially compose them, and then you get around 12 seconds of time. But the best one is really this, where you take part in Q1 and then you take you combine Q2 and then schedule it in parallel, and then you don't then you let Q4 run and then you combine Q5, K6 and K7, but just use their shared arrangement. Do not use lower arrangement, because that will not be good results. There is another design choice like this, which is very close, but it is not optimal. Okay. So you could see that is possible when artificially determined. And that's what I was talking about in the context of class. That why do you combine those components? Because the sometimes give you for the upstate. Composition for all of them is also a very important thing of work. In fact, for next part of talk will be mostly on the part of management. So this is the particular work that appeared in 2010. So here we proposed 3 different types of quantum compositions here. So they have the contribution. One is essentially just combine these two quantum, the type A, just combine those two quantum there. And that leads to more balance of demand of hardware control. But there are all different ways you can combine it. For example, you can do a simple sequential composition, A, where you just call one A, and call one B. And call that one A, one B, or one B. The second one is that you basically distribute this quantity among different threads, but in the same thread block. So, thread block consists of a set of threads. Yeah. So, one group of threads is the thread block, is quantity 1, and another group of quantity, another group of threads, same thread block, is equal to quantity 2. So, that is possible only when you find that in the thread block, there are enough threads. Yeah, that's the third way of parting is either block where you are splitting the model 1 instead of 1. When you find that there was similar data, then you can express the entire block, all the threads block, you can still find 1 block, and still another program thereby then block it in parallel. So what we have shown is that if it is done this way, then they get a significant improvement in moral trust. And these results are related to the reaction consumption when they are actually executed. These are given that executed series. Essentially, you see that they're both of them actually give you good improvement. This percentages on the y-axis is the results that compared against very clear line without it get a simple so if you see a serial without applying here the data model or here so this one It does give you some improvement, but less on conflict activity. That is where there is one. It is the and different combinations again which you different formula. So essentially, software engineering techniques are combined with code in such a way that you can get the maximum, customer of your code can actually get more also. There are workload consolidation, very similar idea. Different essence in the review can actually run multiple workloads and how to work with each deadlock on this can also be different. Therefore, you can have our workload imbalance. You don't have properly balanced all this skew in terms of resource utilization. So that can result in loss of power. And if you can actually pick up that, then it's possible to take the it's possible to configure it faster and at the same time you can see it all. And this particular work from learn so that you can actually both gain from the problem. Now, while so far I've been talking about writing an app or the what about given an application from parallel? That's also a very big challenge. So as you know that the groups are ideal candidates for parallel. But groups, these simple groups that I'm showing here. First one is a group in which you have got two vectors x and y, and assume that it is very large, then call it one variable with one variable, and you are just adding them, and then you will get output vector z. The second one is basically a reduction where you have got one number z, you are summing all the values of x and you get z. That's from reduction. The third one is the matrix multiplication where you have got two matrices. Assume that they are they are all same size n, and you are computing x and y. Now they are all candidates for parallel, but as you can see, there are levels of difference. For example, the first one is very different. The second one is not trivial. It's not that easy. However, it is very difficult thing that is definitely blurred. But if you are expecting that you will write some code or some tool to automatically do it. So why this so? Because if you look at the matrix, the x and y, they are two given. Typically, if you look at the combination of three dimensions, however, they are not given. It could definitely be. So two-dimensional data. But when you look at the ultimately when you look at the processor, there is nothing but a speed. It's all one. You have to basically store that data. We have to choose some order, right? Now, the moment you do that, then the problem comes. Then you have to basically you may have to load one to the row and back, but to improve your data provider so that you don't have to if one element in a row is accessible. Assume that the next element of the same row will also be accessed. So in one shot, if you just load one row, that will save your memory access. That's not easy. But that might also result in a cache miss if the data development is a problem. In GPU, for example, the data is stored in a lower memory and stored in a shared memory. Now, if the data alignment, so for example, suppose if you are storing everyone got data in aligned in some order, and there is a going to access that and bring them to a shared memory. So you know the access them. Now, if the k thread, and k would be 1 to 2000, let's say, if the k thread, more basically half that, half work, we not have time to think what is the voice and what is power. The work is a group of threads. So, for a moment, assume that we have got a bunch of threads, okay? And the k thread, if the k thread is accessible to k locally, and that's true for all k 1 to 100, 1000, then you say that it is a coalesced access. So that kind of access is very fast. You can access very fast. However, if that's not the case, then for non-coalescent access significantly shows the value to get the data from those memory. So now you appreciate that it really becomes a way to lay out the data. So the data is not laid out properly, and the algorithm is not in such a way that the wireless access and to have the problem of electricity data. Even after we take the data into the data memory, there is, then how do you essentially write this code in such a way that two threads are not in the same memory? If that happens, if two threads access the same sensitive band, then we do automatically see the system. So if this access happens one after the other, so your packet will be lost. So these things have to be taken care of. So these are, when these things have to be taken care of, we can program. So data level access is very, very important. Now I appreciate that if I have a multi-dimensional data, so essentially one of the ways to at least to find out whether this particular loop is how much data that is computing and so it is doing what people have used some hybrid computing. That's a more technique to compile. So what happens is that if you look at this very simple loop for I equal to 0 I less than n, j less j, then it's a tensor function, j equal to 0, j less than p, and j equal to 0, j less than n. You are doing this in multiplication here. Now, question is that how many times this entire we take, how many iterations we take, how many times. So counting happens like this. Basically, this function like a box shaped polygon. By another this code, one very long technique is to create a polygon like this, and then it comes like this. It starts from 0, 0, 0. Then it moves to point 0, 0, 1. Then it moves to point 0, 0, 2. While 0, 0, 1 is k, d, and I, and then it goes on, and then it goes to a minus 2. Because it is here, and then goes to the next point. It keeps on counting the points, and after the whole counting is over, then the answer is very clear. Like I think all of them is the size of the loop, or the volume of the loop, or it also is the number of times the loop is executed. And that's important because you need to know, unless you know how many times the loop is executed, you cannot take a decision whether it is executed or not. Okay. And again, this may sound simple, but you do it automatically. There are a lot of decisions. You can only press automatically assign loop, assign the linear loop, very simple linear loop. I equal to 0, I less than n. But if you have n square, it doesn't work because it is not a linear equation. So essentially, from this, the way it works automatically creates a bunch of linear equations. Okay. If you look at the simple code of two level nesting, so it creates two such equations, and these equations form like this. You have got here is this, here is k, and you have got k less than I. So k less than I forms this diagram here. I is equal to k minus 1 to 1. So from this. This is one equation, another equation. So once you have this is dot area that you will count the number of points. The point counting is something that I explained already. If you just count the number of points, then though that number of points is a volume. Okay, so this is how the volume of a polygon and count it. Just like counting the points, and that's possible only in a time, only in integers. So only then you have this function of points, and you use this one there nothing. Here now, obviously you have points. So you understand how much restricted things are really automatic. So if you really have this, you can give it to a solver, and let the solver give you the answer that the number of times you do this is going to be changed. And that's what the points. So, even prediction is also very interesting important area that even a code, you have to be okay, how much is the predicted? Can I predict? If I predict it, then I can possibly very important and very relevant problem that we have. In fact, we have got that problem in the industry. So when they're trying to say that to the artificial code, I have what I believe, can you tell me if my code is going to give ID and still or 10 times still? You have to get the project, you have to say that upfront, that yes, this code, I'm taking it and I'll make it 18 times faster. But the time to communicate money if your code is truly fast. But what if your code is really not parallel? What if the code that is very time is not possible? How do you know? And oftentimes people what they do is that they take the code and move like parallel and after 6 months of effort, then they realize that it's not possible. Or realize it's possible to enormous amount. So therefore, standard problems of using of skills, performance penalty and so on. This is why HPC related to parking and what not really because students do not know how to get it. So, Intel, for example, is not the Intel parallel advisor that is design pattern. Very distinct, but if you use their own pattern, then you can tell you what will be the India-based systems for that work in the past. Any approach is actually oversimplified the data marshalling process. So data marshalling having that copying the data from the host device and vice versa. That's oversimplified, and that oftentimes creates a lot of problems. Focus is a very well-known paper and a tool appeared in a supercomputing conference. And in fact, what they did, they expect is that they expect you to write a skeleton code to the GPU, the target architecture, and from there, it is an analytical model. Yes. So what? Then another approach that is a creation model, you can do the program. If somebody writes a CUDA program, then on that you can analyze and tell what to do the particular. So the last one is basically our work, where we attempted basically predict the CUDA system program without doing any of them. So trying to put it into the architecture, but just understanding that this is possible to come up with some kind of prediction. So that's very quickly. I have given an overview of what are the software evolution part. So the last part for the part taken up by Sam.
So our consumption, that is writing applications for infrastructure for parallelism, not only writing applications that we can optimal performance in the market, but also important features, how we can write more directly efficient applications. So power consumption has now become a first class constraint, and I will show you about three scenarios, three use cases where it's extremely important to write good code that is also energy efficient. We'll also introduce you to certain power terminology and metrics. Also, we'll talk briefly touch upon power consumption and see how we can actually measure power consumed by your code. So this is the first scenario where we talk about battery capacity versus computational demand. So what we do have an exposure of handheld devices, those could be tablets, those could be mobile phones. Now, what has happened is in the last few years, there has been a lot of features that have been added to these handheld devices. But what has still kind of remained constant is the power density of the battery capacity. And therefore, what the problem is that consumers, that is us, we want smaller, simpler mobile devices. But since not much of the improvement has happened in the battery capacity, actually, there is a threshold of 3 watts of power per unit area. That's the power density limit of handheld devices. So what the people are coming up with this new mobile device, what they're doing is the trend is towards higher levels of silicon integration. and smaller submicron process unit. But doing so, what is also happening is that there is a component in the power consumption application. There is something called the dynamic power and also something called leakage power. And by following this kind of design, the standby leakage power that is actually increasing and that is also aggravating to the problems. So therefore, managing power budgets will require aggressive and a holistic approach. Next is cost of data center. And if you look at this chart, what you find is about 40% of the cost of data center is actually being spent upon cooling so as to ensure that the workloads that are running on these data centers can work within those power constraints. So data centers have a large power dissipation and cooling costs form a significant portion of the total cost of operation. And therefore, it is extremely important that we write applications which are power efficient and energy efficient so that these costs can come down. The third is carbon dioxide emission. So most companies today are also being judged based upon their carbon footprint. So for example, there was a recent work that was done by Professor at Harvard who had said that two Google searches produce as much carbon dioxide as boiling a kettle full of water. And that had resulted in a lot of controversies and finally it was Google to disclose its carbon footprint. So now let's look into some of the power availability metrics. So one is power density. So what is power density? It's rate of energy flow per unit volume, area per mass. Now imagine that if you have 200 watts of power distributed by your computation and unit, and it's over quite a large amount of area, then that's quite manageable. And we can have these systems built at very low cost that can manage this. But let's say, imagine this Kepler A50 that has about 225 watts of EVP, and that has a really sophisticated cooling component inside, and that increases the price of this device to say about $4,500 to $5,000. The next is static power. So this is the leakage power, that is basically the power that is consumed by a device that is in the standby mode. And then there is also a component called the dynamic power that is caused by that is power when the device is in working mode. There is also another metric which is known as the energy delay product. This is a product of your energy consumed by your device multiplied by the time of the runtime of that application. So it gives equal weightage to both perform to energy as well as performance degradation. And since it's a product, so therefore low EDP values are always desired. So now let's look into this chart, which is performance power trade-offs. So what we really want is to write an application that will not only cause performance loss, but also power loss. So we don't want to write an application that's going to be in this wide zone. What we really want to do is write applications which will not only help us gain performance, but also at a very low carbon footprint or without causing minimal power losses. This green region, so it shows that we can get some gains in terms of energy consumed by the application, but with some kind of a performance loss. A typical scenario where this happens is when we use something called dynamic voltage frequency scaling, so as to reduce the power consumption by the application. And again, this volume is an area where you have the energy loss constraint by performance gain. So now let's look into the CMOS power consumption or dynamic power. So this power is a product of activity factor, the capacity of the device, the capacitance of the device, square of the voltage, that is the operational voltage, as well as the frequency. So what we see is that if we can reduce the supply voltage, let's say if V is the supply voltage now, if we can make it 3 by 2, then the power also reduces by a square of that factor. But if we were to reduce the operational voltage, then what happens then also comes at the expense of operating frequency. So this F max, that is the maximum operational frequency, that's actually proportional to V minus V threshold whole square divided by V. So if say the supply voltage is quite large when compared to the threshold, then this F max is roughly linear in width. So therefore, if I happen to reduce the supply voltage, then it also puts the circuit at a lower frequency. Also, what happens is that reducing V also requires a reduction in the V threshold because V threshold is threshold voltage which is consumed by the device or which is used when the transistors are still in the switched off state. And therefore, what happens is that when we have this reduction in voltage, now when we have a reduction in voltage, the speed at which the transistors switch, so that also tends to come down, and therefore we need to maintain that speed, and therefore the V threshold also has to come down. So but then bringing down the V threshold also increases the leakage current because this leakage current is inversely proportional to the V threshold. Therefore, it would make this leakage term appreciated. So, if we were to summarize, then what we see is that reducing the supply voltage has a significant effect as to on the power consumption, and but parallel processing can reduce this. Therefore, it's the power consumption that can be reduced efficiently. Also, reducing the supply voltage can increase power consumption, but then what happens is that the leakage current increases, and therefore this technique, so we kind of still need to find out how far this technique can be applied. Now, let's look into how power can be measured when application is being executed on the system. So, with the centigrade architecture, we can introduce something called multiplication of the running average power limit. So, this is included in PAPI or the performance API. This is an open source API. And now, if you want to kind of find out the power consumption by let's say a particular function in the code when it's being executed on the system. So, what we need to do is that we need to create a PAPI event set. And so, this is how we create this event set. And then we add certain power events. Finally, we have to start profiling of these power events. So that's done through a API as well start. Then we call our CPU function. So all these have to be done on the same thread. Then we can stop the collection of power events using a PAPI stop. And finally, we can query the values that have been collected in the power events and find out what has the power consumption by the CPU. It was executed at a particular circle. If we were to compare this with how the methodology is with GPU, so NVIDIA's GPU is supply something which is something known as the NVIDIA Management Directory or the NVMe. So it's a C-based API for monitoring and managing various states for the NVIDIA's GPU devices. So here what we have to do is that we have to have two threads. One thread is going to query the GPU and find out what is the power consumption on the device, whereas the another thread is going to run the kernel of the GPU. So, just to kind of give you a brief idea of what a kernel is. So, kernel is a set of instructions that are being executed on the GPU. And so, what happens is that while a kernel is being executed on the GPU, if you happen to plot the power consumption, there are different timelines you have different power consumed. So, therefore, if we were to kind of find out what is the power consumed by the CPU, so then there are certain API functions that are available in the NVIDIA Management Library. So these are some of the APIs. So NVMe device get power usage helps to find out the power usage in milliwatts and its associated certificates will also include the DDR5 memory of the GPU. We can also find out the thermal components of this device. For example, we can the current temperature readings for the device. And also we can find out the minimum and the maximum power management limits that are there for every GPU device. Now, having an idea about how to measure power, both on the CPU as well as on the GPU, next step would be to find out ways in which this dissipation can be reduced. So, a common power reduction technique is known as DPFS. So, DPFS stands for dynamic voltage frequency scale. And within that, we are going to do something known as DFS, or dynamic frequency scaling for both CPU and GPU. Now, the power that is calculated, so that also has a component known as capacitance. So, how we can reduce the effective capacitance of the device. And also, we will show you. So, we have this molecular dynamics application where which we were employing a large number of reduction kernels. So, we had studied DFS technique on this reduction kernel. So, we will present certain lines and show you how effectively this technique can be deployed without causing any appreciable loss of the performance of the application. So, power reduction technique, so as I had talked about earlier, so this is E is equal to the capacitance into square of voltage with the activity factor multiplied by the frequency. So, reducing voltage also reduces power by the square of that factor. But what happens is that if you reduce voltage, the frequency also comes down. Therefore, if you were to assume that power reduction could be in two ways, but then the reduction in energy is not included because as the frequency comes down, the time taken for execution of that application also tends to increase. So therefore, downside is that it can linearly degrade performance. But it is still appealing in certain scenarios in which the application is more memory bound rather than compute bound. Because if it is memory bound, then CPU frequency can still be decreased without causing any, without hurting the overall performance of the application. So now let's look into how programmatically or some software approaches into bandwidth frequency scaling for CPU. Now this is something that we had largely on the Linux operating system. So the Linux kernel provides a kernel module which is known as CPU FREQ, and that allows bandwidth frequency scaling. So this particular kernel module has a set of governors. So a governor, something like an on-demand governor that helps to manually switch between CPUs available. The CPU load goes beyond 95%. There is something called performance governor, which means that to run the CPU at the maximum frequency specified by the manufacturer, there is something called conservative, wherein manually switch between CPUs available that has 75% load. There is also something known as power save, which is to run the CPU at the minimum frequency specified by the manufacturer. And finally, it's user space. User space will allow us to run the CPU at frequencies. There are a set of frequencies that are specified by the manufacturer, so you can skip one of those frequencies and run the CPU at that particular frequency clock cycle. Now, there are also certain command line tools. For example, there is something called CPU FREQ, which prints all available frequencies as well as the current frequency of the CPU port, and then the CPU frequency set that allows modifying the CPU frequency set. What I want to mention here is that these techniques or the DFS technique can be done on the fly as your program is executed. That is also possible. Now this is so these API functions that we have listed here in this table, so they are quite documented, and you can go to a Linux system and you can check this header file CPU frequency.html. So there are APIs which first is going to check whether the CPU can browse DFS or not, then query for the frequencies that are available. Also, it can give you a list of available governors. You can change the governor and you can also set the frequency from the list of frequencies that are available. And you can run to a particular application on CPU by setting the frequency. Let's now look into how you can do a program level DFS for using the NVIDIA management library. So on CPU, you can do DFS on the front, but on GPUs, that is not possible. So you have to first set the particular frequency of the secret code, frequency of the memory part, and then run the kernel. And after which, if it's necessary, you can reset back the GPU code frequencies at its original values. So to do this, NVIDIA supplies some APIs which are kind of pretty much similar to what is there on the CPU frequency. So you can check if the GPU supports DFS. You can get a list of all possible graphics slots that can be set. You can also get a list of possible memory clocks that can be set. And finally, you can also set the clocks that include graphics applications to be running. Finally, so after DFS, so DFS is a technique in which we can reduce our distribution. But how about capacitance and active factor? So can we do something to get power reduction based upon certain techniques with capacitance and activity factor? So there are certain kind of architectural techniques that focus on dynamically optimizing the switching activity. So these architectural techniques are based on certain models, and there has been good amount of work that's still going on in this field. But what essentially is required is that can we reduce the excess amount of switching activity that happens within the circuits. So you can check if certain units are idle, and if they are idle, for example, have different cache levels. If we know that our application is not really particular cache level, you can straight away turn off those cache levels, thereby save power. Second is we can also check for idle bit. For example, if we have a particular bit and we are working on say some numbers which are let's say 8 bit or consuming 8 bit, then the rest of the bit of the bus that's not effectively bit. So one way is therefore to turn off all that, and that can be done actively. Or we overload the bit, adding more number of such instructions, such 8 instructions, operations at a time. We can also look for to check whether capacity of large structures is being utilized. So here structures basically use the wire which is granular signal. So can some of those wire lines be turned off? Also, there is a lot of speculative caching that happens, and typically these kind of things happen simultaneously. But there is just going to be one hit, the rest will be all missing. But still power is being consumed. So can be kind of sequentialized rather than doing all these speculative caching in parallel and sequentialize it so that as soon as there is a hit, there is no further speculative caching. Also, there could be certain repetitive classical activity. If there is something of this kind of thing happening, then it can be memorized close. Finally, also can we kind of find a way to reduce the work performed during misspeculations. Now let's look into a demonstration of DFS. So what we have done is we've taken a reduction kernel in a particular dynamics application, and we had run that on this Tesla K-Win CGPU. So this particular GPU gives us these set of frequencies, memory frequency as well as the graphics frequency. And this Tesla K-Win has 2496 cores, and its CPP is about 225 watts. Now reduction operation, so this reduction operation was done on 420 data elements and the data type was double. And since this is a reduction operation, so it's more of a memory bound operation rather than the compute bound. So therefore, we can reduce the dose frequency of these graphics cores and save power without hurting too much of the performance. So what if you look into the reduction kernel that's supplied by NVIDIA, so there are different reduction kernels from the most highly written one to the most popular written one. And what we did was we took for each of those kernels, we had profiled those kernels to try to find out what is the peak power consumption, what is the energy consumption. So over here, we have listed down the comparison between the most highly written one versus the one which is most optimal. And what we found is that With the high written kernel at 2600 megahertz, also graphics frequency of 715. So with this, we got the best performance from the most mild reduction kernel. But its peak power consumption was about 65 watts. The energy consumption was 12.5 joules, and the energy delay product is equal to 0.2 kilos to 0.03. Now we took the most optimum reduction kernel, and we found out in this optimum reduction kernel, in order to get the least power consumed by the device without hurting the performance. So this was done empirically, and we found that at 3.4 megahertz for both the memory frequency as well as for the graphics core, we got peak power consumption of 26 watts. The important thing is this energy delay product. It's a significant reduction in energy delay product. So therefore, it's not only important to kind of find out or guide optimize the kernels to ensure that we get the best runtime from the device, but at the same time, we also need to investigate this thing. We also need to do DFS to find out at what memory frequency and at what graphics core frequency can we also get the minimum power consumption by the device. Thank you very much.
We are almost at the end of the tutorial. What I will do is I will very quickly summarize and essentially tell you what are the important research directions that one could take. We talked about the upstream design support, which is very important for writing efficient neural programs, but also supporting the end programs. Essentially, there are quite a bit of work that needs to be done, and it's still a kind of a nascent stage. Essentially, for the enrichment of this programming instruction, even at the task areas, with task model, that itself is a good area to work on where you can actually improve that particular library. There are, we can do work on design assistance using parallel patterns. That's also a very important area of research. In fact, modeling those, can we have a visual design metaphor the way we are familiar with the sequential programs like UML and stuff? Can we have very similar visual design metaphor where we just design the application visual and then things get translated to a code automatically? Can we have that? Then at the language and the library support level, we still have a lack of a single software abstraction, be it library or a language, which can cater to diverse architecture like CPU, GPU, etc. One attempt was made in trust, but still enough work that one can do there. Lack of ability to get the unique breakdown of core consumption at software level is still not possible, which is why people are requiring a lot of empirical models to predict how much power that's consumed by different units. In fact, the lack of holistic software power management techniques are still not available there. Even though holistic hardware power management approaches exist both for smart complex architecture as well as ARM CPU, but there is still a shortage of the software approach, and that's very important for all domains. In terms of optimization techniques, as Shanta was talking about, that it is actually a problem that given a set of kernel that I write, what is the best configuration? What is the best configuration? Not in terms of just the amount of resources that I'm going to allocate to this particular kernel, in terms of number of threads, number of registers, number of blocks, but also the amount of frequency or the optimal frequency, what is the optimal voltage that it use, so that ultimately my power and performance is optimized. That's the same. So power prediction, if that's possible, then that can be used by different power schedulers, both in HPC as well as the group and so on. The automation of power techniques you get the state at a present stage. In fact, this can be multi-objective analysis, and obtaining a paradoxical solution is a good area of research. In terms of transformation techniques, transforming the code from sequential to GPU and specifically GPU transformable code. So we talked about something like which is inversely parallel, which is very trivial to prove. But there are codes which are GPU portable, like kernel, like your reduction kernel or even native modification, some variant of that, which are where it is possible to reduce it, but it is not that trivial. So can we have some algorithms which can take such codes and automatically transform at least piece of development hints, and even implement ready for both power as well as the speed. These are the at least at a very high level to be an interesting area of research in this scope. So that's it from our side. Thanks for listening. So if you have questions, we will be happy to answer. We are here. We can also answer it offline.
Well, actually, in the stream processing portion of your presentation, you notice that first one the portion of this algorithm in the key. So can we do that simultaneously, pushing and popping at the same time? This is a restriction I believe was pushing all those elements and popping.
No. I did not say that you have to push and pop sequentially. All I said is that in schematic language, you have a special concept of push, pop, and keep. So it's up to you to the way you want to use it. So in that particular example, what happens is that suppose you want to do a processing, right? If you do the processing, then obviously you have to the pop first and then do the work. Now there is a implicit about unless you really get the data, you really have to it. But your question is that suppose I have got multiple data. Why can't I do it parallel? Of course you can do it parallel. And that's what is the implied thing. I mean, what I said is this is a data parallel language. So what it says is that you do a pop, then you do some operation, and then you push. But this particular sequence of pop, execute, and push can be done in parallel on multiple data sets. And that's implied in the language.
Okay, that means like I have 10 data which I will push. And I'm operating on them as well. And that's me technically I have data being pushed in the system.
Yeah, that's possible. Yeah.
Dr. Sir, I have a very basic question. You are saying that we are parallel processing. There are various processors, code to Neo, then dual code like that. But we have a single operating system which has single kernel. So whenever we are processing any process parallelly or processing multi processes in a parallel way, but as we have a single kernel, so how can we increase the processing power as per the processing power of that processor? As we have only single kernel.
By kernel, you mean what? I mean the GPU kernel or OS kernel?
OS kernel.
So see, what happens is that in the OS kernel, you have got process schedulers, right? And even before this multi-core and many-core existed, there were different schedulers which would give you an illusion of the multiple processes running environment. These were multiple ones, right? There are all this time-specific scheduling and so on. So essentially, with the multi-core and many-core, what's happening is that these guys can actually take help of this course and have threads. Those threads are actually allocated to different CPUs, CPU cores. And each thread can execute a particular process.
It's all right, but whenever we are going to execute the system command, at that time there is a kernel. The kernel thread cannot do that thing.
Well, I mean,
system call means system call. Whenever any system
so
call
ultimately your system call will be executed as some instruction, whether you call it as user instruction or something. But at the end of the day, these are all instructions which are binary codes, right? They're all either recipe or things like that. So those things will also be disabled there. I don't understand why that would not be possible. Of course, if you are making a system call, that is simply if you're making an IO call, right? And the IO call is not parallelized, then things will be shown, obviously. But if you're writing a pure system call application, but you don't have such command call which actually demand for the IO, which is serial in nature, then you can of course utilize the codes.
but if there are multiple system calls, then as we have single kernel, so only one system call will execute at a time. There will be no parallel processing in terms of system call.
As I said, that if your system, if okay, suppose you have got a very powerful IO, okay, a very powerful disk, which can actually handle multiple requests at a time, then of course it can be done. I mean, when there is a stream of IO requests coming in, they are all parallelized, or not even take care of them.
It's a means that you say that there is a modification of kernel or there is no impact of that processing power on the kernel.
The impact of processing power of the kernel. I don't really understand it, but honestly, today at least all this, be it Linux or be it Windows kernels, they are all multi-core aware kernels. It's not that they are not aware. So they definitely develop that to process parallel. But as I said, that if the architecture, if it's ultimately given, it also device level. If the device level is quite powerful enough, right, to basically take care of the IO calls, then it is certainly possible.
Now I request for actually please respond. And,
Any other questions?
So as you told that whenever we want to finalize the particular application, we are hopping from CPU to the GPU. In that case, PCI have heavy limitation. So, what is the use of using high power GPUs like Tesla, Kepler, or Quantum?
Right. So you have to remember that the kind of applications that you want to run on the GPU, so they are compute intensive, which means that you are kind of assuming that the time to copy data from the CPU to the GPU and the time to run that application as is on the CPU. The time to run the application on the CPU is significantly more when trying to copy the data between CPU and GPU. What happens is that because the GPU design is equal to inherently exploit the data parallelism in that portion of the code, so the execution time on the GPU comes down by the factor will be, let's say, 5, 6, 10, 100, whatever. In that case, what happens is the data transfer time that becomes now the dominating factor. So therefore, we are talking about speed up predictions, we are talking about trying to ensure that we are able to get the maximum out of these co-processors. It is also important that we minimize the data transfer costs so that the entire application running on this individual architecture, that runtime is on. Yes.
now we'll break for 45 minutes. And after that, we'll ask you for any questions.
वीडियो कैमरे बंद किया